start the tech presentation.
All right, so good morning. Thank you for joining us for our Tech Talk. And today we'll discuss the university R&D and deployment or deployments of robotic systems at the DOE facilities. Obviously, this is the work that's being done here at ARC. Myself, Leo Lagos, the principal investigator for the DOE EM agreement, and our colleagues, Noy McDaniels and Anthony Abraham, which contribute to these efforts, as well as many of the students and the full-time staff at ARC. So with that, the way we'll do this, I'll present half of this, and I'll leave the hard part for Anthony to present, so I'll present the easiest stuff. And then if there's any questions, I guess we can leave those to the end. We do have a good number of slides, so hopefully we have time at the end for any Q&A. But if not, feel free to contact us if you have any questions. So this is my shameless plug for FIU. So large Hispanic university located in Miami. We do research, so we are ABET accredited, and we have about 58,000 students. Every morning when we open the doors to FIU, the work is being done at our facilities here at the Applied Research Center, our Applied Robotics lab. Again, I'm the principal investigator. We have the lab managers and also the research scientists that contribute toward the DOE EM, DOE LM, and other DOE EM funded research, as well as NEUP, nuclear energy and university programs. I mentioned the MSIPPs, Department of Transportation and Science, NSF, National Science Foundation, and our DOE fellows, our LM fellows, and our students, research assistants. You see them all listed there. So that's a large number of students. We have 3 labs, really, that are dedicated toward the development of robotic systems for EM applications. As you may know, our client, the Office of Environmental Management and the Office of Legacy Management, so we support the mission of DOE EM and the cleanup activities across the DOE complex, across the nation. And we recently started working with LM in terms of the stewardship of those facilities as we move into the future, right? So we're going to have to keep monitoring the facilities that have been cleaned up by DOE EM. The way we do that is really a 3-pronged approach. We have FIU students, faculty, staff at the Applied Research Center on the left side. We have our colleagues from DOE EM in Washington, and also the site offices that obviously fund the program, but also give us technical direction as well. But the most important piece is the middle, which are the field offices, the national labs that we can collaborate with at the DOE facilities, and the end result, which should be a field deployment of the technologies, methodologies, and the studies that we do here at FIU, should have an end goal of supporting the sites directly to advance the DOE EM mission. More specifically, how do we do the technology transition, the technology transfer to DOE sites? So we directly collaborate and engage the stakeholders at the site across the complex. In terms of stakeholders, we have DOE EM. In Washington, we have Kurt Gerdes, our TD office director, our technical monitor, Ian McKinley, assisted by JP Cabon as well. And we have the stakeholders at the site, right? Hanford, the double shell tanks, single shell tanks. We have the DOE EM field office there, ORP, and Eric Nelson, and our colleagues at WRPS that we work with on a daily basis, really. The same thing for LM. We have the federal support from Yelena and David Schaefer, and some of the collaborators at the LM facilities. We have a close collaboration and engagement with all the stakeholders in terms of project technical plans. We tell them how we're going to execute the work. We report monthly, quarterly, yearly. We have monthly calls. We have a dashboard that we're talking with the headquarters. That might be another way to communicate the progress of the corporate agreement to DOE. So that's in the works. We have technical meetings and calls throughout the year. We have site visits, site training. We do demonstrations of our technologies at DOE facilities, proof of concept. We do community outreach to let people out there what is it that we're doing. We do technology transfer, which is the end goal, right? That middle piece that I talked in the previous slide. The mini rover, our technology going to be to WRPS in Richmond as a deployment and technology transfer, as well as the other way, right? The Husky platform that WRPS will loan us for a little while so we can work on developing, optimize the technology. We participate in conferences, workshops, DOE EM-led activities such as the interagency agreement and the FRTR, multi-agency type of agreements that they have. We have professional organizations that we're part of, the ANS Robotics and Remote System Division, as well as the ASTM International and international engagement for the knowledge transfer. So we work with the AEA in Vienna, AEA in Paris, CARI, South Korea, as well as IFI, the Institute for Energy Technology in Norway. In terms of the workforce, the training and knowledge transfer, we work with the students, DOE fellows, that go to summer internship at the DOE facilities, they identify problem set that we can work with, and they work through the summer, and then they bring that back. And at the same time, we're transferring that knowledge, not just from the people here at FIU, but also from the site, mentor that the fellows have during the summer. And during the summer, as well as here at ARC, we provide the students with how do you transfer that technology, right? So all those are all the steps. The concept, FIU, to send it to the site, and then ultimately to transfer that technology to the site so DOE contractor can use in support of the DOE EM mission at the various sites. This is our technology roadmap. All this current technologies that we're working on, and when those technologies are going to be deployed, in the field, whether it's Richland, Savannah River, Los Alamos, Oak Ridge, the mini rover. We have a green all across the board, all green. We have done all those things. We have done the internal in-house development, deployment, testing. We have done the site deployment in 2021, and then we went back in 2022, and that technology was officially transferred to DOE EM through WRPS, which is the contractor at the farm tank. So a check for that, and we're following the same process with all the other systems that we're currently working on, the ones directly funded by DOE EM, as well as the ones funded by DOE LM, and also some other programs. Is what we're working on, and what you see in red is the next step, right? And all of the next steps will be the site deployments for each one of those technologies that you see there, supporting the tank farm at Hanford, the Gage Canyon at Savannah River, WIP, the waste isolation pilot plant, LM, the rifle cell, as well as the Sandia project in terms of wearable robotics. So that's the technology roadmap that we have within the next 5 years, right? The corporate agreement is funded in a 5-year cycle. So from 2020 to 2024, that's where the cycle that we are right now, and those are the technologies being, transferred or about to get transferred. So in terms of the presentation, I'll cover the first part, and then Anthony will cover the second. So we'll talk about some of the deployments that we wanted to, discuss here. The first one being the deployment of the mini rover at the AP-105 double chill tank at Hanford, which we did in 2021 as an initial deployment, and then a full deployment in 2022 March. As you're familiar with the problem set, most of you know that the tank farm will have 177 total tanks. 149 of them are single shell, built between the 40s and 60s, and 28 that they were built in the 60s and 80s, which have 28 tanks there. So 56 million gallons of radioactive waste. All that waste is stored below grade. So any inspection of those tanks Obviously, we cannot send humans there. We have to use a robotic system, and very small robotic system, and that's why we developed the mini rover, right? So this is a magnetic tool that adheres to the bottom of the tank. So we send this system through a vertical deployment. Then once it gets to the bottom of the tank, the mini rover can go and inspect the air lines and the refractory pads and look for any type of contamination that we can find, any type of visible things that we can see. We have a video camera all part of this, and this is a patent pending, so we have disclosure on this system. And I believe the next slide has more details. It's just a control box and the inside of the control box that makes the whole unit. So the mini rover plus the control box, that's what it was transferred to WRPS. This is in-house testing that you see on the left. You see the right side, which is the picture of the bottom of the double chill tank, and you see the corrosion, some of the debris that you're going to find when you go there. So we have corroded surfaces. We have elevated temperatures, about 130 medium temperature. You can go a little higher. So all those things that we needed to take into account during our design. And what we found out throughout the development is that we have well seams that they were proved to be challenging. So we have to redesign our original system. Let's just give you an explanation of what we have here at FIU as a large-scale mock-up. We duplicated the heat issue by putting some heat sources here. This video here shows you the mini rover going in our mock-up test that you see here on the bottom. And the importance of the mock-up is to be able to test the technology before we send it to the field in real life conditions, right? As closely as possible that we can duplicate what this unit will see once we deploy it in the field. So the importance of large-scale mock-ups that cannot be seen. Also, rust at the bottom of the tank. There's quite a bit of rust. So we wanted to see if we have any type of rust buildup in the wheels. Remember, this is magnetic. And if there's too much rust, maybe it's fall. So we tested that extensively here at FIU, as well as once we deployed it there. So this is the actual deployment. This is back in March 2022. Anthony and then our colleagues here from FIU, including one of our fellows, Jeff, they went there in March. We had a cold test at the WRPS facility, and that was two purposes: show the capability of the technology, and also train the workers that were going to operate this the next day. Obviously, we cannot operate it. They have to have their own people operate the system. So we have to teach them how to control, how to maneuver the system. And we made it really simple for them to do that. So we're extremely happy with the, not just the training, but also the deployment. So this one shows you two things. The operator on the left trying to align it so we can go under the refractory and those channels. So the video on the left,
all right, back out.
The joystick, and then the video on the right shows you the actual picture that the video after the demonstration. So it was extremely successful. We proved the proof of concept was beyond, I guess, proven that this system can be used. Now this technology has been transferred to WRPS, and they're using it in the field. So the video on the left is just showing you when that unit went in, and then obviously the one on the right.
PR shots.
All right, I guess we can listen a little bit of the reaction of the operators.
Come on back. The PR shots.
They're just trying to record all here on the screens.
You can take my word for it, but I'm really excited about it. And you see the rust? So some
looks great, man. Looks great.
We would have high fives and all kinds of good stuff. Rust accumulation on the wheels. There was some rust, but our design airbag will scrape the rust as we did. But even with that, even it was close, it was able to bottle the tank, and we never lost contact with the right. So very quickly, another thing we want to do is use an ultrasound sensor to detect the test for the integrity of the tank. So these are just preliminary in-house lab testing that we're doing, trying to find the use of the ultrasound sensor. As you see, the shape of this mini rover is different from the one that you saw earlier that was deployed. The other one was a V shape. This one, to accommodate the ultrasound sensor, we had to make it into a U shape. So this is what we call the U-shaped rover. Another deployment that we did this year, we did a cold test at the Hanford cold test facility. This is for the lateral gamma. This is for a single shell tank application, different from the double shell tanks. There is this pipe on the bottom of the tank. Again, access to the bottom of the tank. Obviously, humans cannot go there, so we have to develop a system that can do that. And we want to measure any type of leakage, radiation, whatever we can find. So we'll have a gamma scanner, as part of this technology development. So this shows you the tank, the dimensions of the tank, how deep below grade we have it here. The lengths of the pipes are about 140 feet. And they have different lateral, sections here in each one of those tanks. So each one of them has 3. And we have to inspect each one of those. This is a previous deployment that was done in 2005. They did use a gamma radiation sensor, and they used another system that they developed, and they were able to inspect the laterals underneath the single shell tank. WRPS wanted to do this again, so they came to FIU, and we have previously developed a pipe crawler, a peristaltic crawler. So basically, our job was to adapt that for this new application, take into account a payload, which was the radiation sensor, the gamma sensors that we see here as the payload. And we added a camera and a lidar system as well as automated reel system that will be able to deploy. So the payload is really the radiation sensor. Ours is a mock-up. It's not the actual sensor, but it's 15 feet in length, almost 2 inches in diameter, about 3 pounds on each module. So we have to drag at least 9 pounds. So the payload is about 9 pounds. We'll hold this over here, and the backup camera and the lidar. So we're looking at least a 10-pound system that we have to introduce into the pipe, go 140 feet, and then bring it back. This one video shows you the pipe crawler with the mock-up module. This is just the in-house testing that we did here before the deployment. And I believe this video might show you the reel that we have to automate. So off-the-shelf component that we updated, so we can have that synchronization between the reel and the pipe crawler. So we have the students, our full-time staff working on the reel before the deployment, and then the in-house testing of the crawler. We had already extensively tested the pipe crawler for other applications, 6-inch pipe and 3-inch pipe. So the challenge here was the adaptation of the mock-up sensors and the 9 pounds of those sensors, plus the automated reel for the extraction and the deployment of this unit. This is the actual field test that we did. It's a cold test, so it wasn't inside the single shell tank. So we worked with WRPS, and they created a mock-up in one of their facilities, just outdoors. And our colleagues here went there in March to test it at their facility. So we have to make sure we can mock up the below grade, going all the way to the bottom of the tank. So that's why we have to use this type of, they have to use this type of scaffolding. This is the testing there at their facility. Is testing the pipe and the reel. So that's synchronization. I think there was a here in the computer synchronizing the length of the cable as this thing moves, and it tells you what in that pipe here and the type of distances. This is another picture of the mock-up. We have videos here. We have MAC here on the top of the scaffolding. This is all the way down, and then we have the elbow on the bottom, and then we have the transition from the vertical to the horizontal through an elbow, which you see here in this picture. So this is already being, fed from the top, going all the way on the horizontal length of this mock-up. And Anthony, I think that was all 140 feet.
Yeah.
Right. Okay. So they mocked up all 140 feet that you'll see in the actual tank. And again, that was also a good, very successful cold test. So we learned a lot from this cold test. We brought the unit back. Also, this past summer, we have 2 students there that work with WRPS engineers the whole summer to optimize the reeling and also the pipe crawler. And right now, we're just waiting on this actual gamma radiation sensor. So once they have that, that's something that they're going to procure, and then they will probably send that to us so we can adapt it to the pipe crawler and finish the technology integration, and then we're looking at the technology deployment sometime next year. So this is the team, successful deployment. I'll just very quickly mention this. This is some work that we started with our students that they were there, our DOE fellows. They were at WRPS this summer. This is so really this started collaboration 2022 in the summer, and this is for the purpose of using a robotic manipulator to perform authorized sampling high-level waste tanks. So we did send the UR5 with the students over the summer. Here we also did an in-house development of the frame to hold the robotic arm, so we can go upside down and scoop, mocking up something that this robotic arm would do inside the tank. So that was Joel's a lot of the work, and Josue also contributed to that this past summer, and that became a task for us that we are starting this year. I did. What did I skip now? With the video.
Yeah, the next one.
This one. All right. So Anthony told me that I skipped the video. So let's play the video here. I think this is Joel. At the end of his internship, he demonstrated his proof of concept of what he had developed and worked on the whole summer. So not sure if this is going to play. It doesn't play. All right. So you get the idea. So we're going to jump to the next project. I know I'm stealing from Anthony's time, so very quickly we'll mention the H Canyon work that we're doing at Savannah River. The H Canyon is really the facility for reprocessing waste. This was built in the 50s, and between the building and its stack, there is a tunnel that filters the air or transfers the air from the glove boxes in the building to the sandbank, and then from the sandbank up to the stack. So that tunnel is what you really see here. Obviously, because of the nitric acid in that airflow, the walls of that tunnel is deteriorating at a rate where Savannah River has to look at the rate of deterioration and see if this structure is going to continue operational for the next 20 or 30 years. So that's the biggest challenge they have. Obviously, this tunnel is no entry at all of humans, only robotics. They do the inspection every 2 years, where they send a robotic system into the tunnel through a manhole, and then they inspect the tunnel. And they have done 5 deployments. They have sent 5 units there. 2 of them got stuck, so they were able to retrieve 3 of them. I think one's still there. So obviously, very, very challenging environment. There's the tunnel have 3 fans. When those 3 fans are all operational, I believe it's almost 100 miles an hour wind. I think for maintenance, they shut down 2 of the fans. They only have 1, but even with that, you have 30 miles an hour wind going through that tunnel at all times, because the air has to move, right, from the building to the stack and passing it through the sandbank. So that's the challenge. So here we did 2 things. One is studying the conditions of the concrete that we think is is present in the tunnel. So our colleague Mayron, he's been doing some studies on the concrete and trying to duplicate that concrete surface. So she's been exposing concrete samples that we use the same consistency of the concrete that we think that tunnel was built with, and exposing that to nitric acid and developing the different surfaces based on exposure and accelerating aging of that concrete that we are doing. The other thing that we're doing is we're developing the robotic system that's going to go in that tunnel to be able to really not only inspect it, but ultimately repair it. Because we have to repair this facility. You know, we cannot shut it down. We have to continue working for the next 20, 30 years, or whatever, 50 years. Obviously, if the concrete is deteriorating, the structural stability of this the facility is compromised. So DOE has no other choice but to fix it and repair it. So the holy grail is to build something that remotely can repair these walls in the tunnel. And that's what FIU is doing. Here we are doing the concrete work, but not only the concrete work, but we're working on a system that we call it a wall crawler that eventually will go into the tunnel, deploy that remotely, and repair the concrete, obviously inspected and then repair the concrete. It's a very challenging problem. I think in our roadmap we have that as a 5-year plan with a potential enrollment after 2024. But again, there could be a number of challenges that we have to overcome. This says specific city, you see the wind, but nevertheless, we're able to and even onto the ceiling. So Mac and Son's been working on that, and we are in, I guess, on the robotic system development. We can make it climb. Obviously, now we're working on the actual spray mechanism that's going to have to be mounted on the platform so we can spray whatever material we're going to be able to use for fixing those surfaces. Very quickly, I'll go into the glove box automation work that we're doing. Starting with the site our 5 robotic system. We build a mock-up glove box, and we just make sure that we can potentially in the future use humans instead of and that was the whole objective of that first phase of the project. We did a lot of human studies in terms of fatigue. As you can imagine, a glove box is not built for every shape and size. It's just a standard glove port that you put your hands on and you work manually and able to do any type of task inside the glove box. Cleaning, with transfer of high radioactive waste from container to container. There are a number of tasks that they're done on a daily basis at DOE facilities where they use glove boxes. We just try to automate that system, not to replace the human, but to add something that can help the human in this dull, dirty, and dangerous task, right, in 3Ds. So we just assisting the humans in terms of doing this type of work. The thing that we're working and I believe at this point I will turn it over to my colleague Anthony for the rest of the presentation.
Hello, everyone. I hope you can hear me well. So starting an SIPP project, we create this research area in environmental robotics, and we have success several projects. So we started in 2019 using a base framework for mapping, this autonomous platform. Then we moved to tank farms in 2020, and then also you expand that to drones in 2020. Then attaching the same network of sensors to drones. And then currently we are expanding this even further to automate inspections at WIP and also to investigate climate issues in the LM site disposal cell. So the task is long-term surveillance of nuclear facilities and repositories where we get platforms of the shell platform. They could be wearables, drones, or ground platform, aero platform. And then we instrument with a bunch of sensors. And this can give you a sense of the environment and also other sensors that allow us to measure, for example, humidity, temperature, and heat. And then we develop autonomous systems, state-of-the-art algorithms that allow us to map those facilities in a way that we can alleviate the burden of people suiting up and going to those places to do routine inspection of those facilities. So here is an example of one of this work that we did with LM. So LM has several disposal cells around the country, and those disposal cells are designed to last 200 years at least. Some of them are already showing some erosion, underground erosion. And this underground erosion was detected with a slight depression of the soil. And so now FIU is helping LM to try to understand how this mechanism works, and thought also to evaluate the state of the erosion in some existing cells. It is very interesting because despite the Southwest being in a terrible drought, they have few rain events, but now they have stronger rain. And then there's a concern that even though there's less rain, however, the strong events are affecting the rain and take them away from the design criteria. So to monitor climate change, it's very important for us to have awareness, assess the conditions, plan, implement solutions, and also monitor and evaluation. And FIU is helping with the monitor and evaluation. So we have our framework. Our framework, we use mobile platforms, ground or aerials, and also sensor fusion. So those platforms carry a bunch of sensors, Lidar, 2D camera, video, environmental data, photogrammetry, ground penetrating radar. And then we try to build a digital twin. With the digital twin, we are able to analyze the facility over time. Then also we are creating data time machine algorithms for us to automate the detection as well. Not only to automate the capture, the building of the digital twin, but also the analysis of this digital twin. What is important as well is provide to the inspectors ways to inspect virtually these digital twins, and we are using virtual reality, augmented reality for that. On the side, we also use weather trend analysis using publicly available data set. And then we are also add all of these, the digital twin and also the weather trends to hydrology modeling. And then we try to predict what's going on in terms of the effect of climate change in those. What's important about LM that everything has to be non-destructive. We don't want to excavate to understand what's going on behind because you can have exposure, radiological exposure. So what is the digital twin is? Digital twin is a virtual representation of physical product or asset. So we have a digital model that represents actually the facility. And then we use in the first stage of this project, we're using aero Lidar and photogrammetry. So they're very flexible platforms. We can add as much sensors as we want. And then we are adding cameras and also Lidar to it. Here is our first deployment that we did at LM, legacy management. You can see here we purchased off-the-shelf drone, and then we developed a Lidar data acquisition system. You can see here on the bottom the Lidar and the embedded computer for visual data. This was developed at FIU. Here you can see our prototype, and on the side the electronics and the 3D printing, the mounts that we have developed. All of these were developed by students, and then we were able to develop this, test it in-house, and also went to deploy to LM. So we did our first deployment was to the rifle cell. It's about a 701 acre. And then you can see here, of course, deploy something at LM, DOE site require a lot of testing and planning. And then we have to comply with Federal Aviation Administration regulation. We have the student has to obtain a pilot license. We have to perform a safety plan to be able to do that. So you can see the student working on his data module. Then 2021, we went to the site. We went in a crew of 5 people. And then you can see here some pictures about the deployment. And the student was the pilot chief in command, and he performed the whole inspection. You can see a picture of the drone flying the cell. Now, this is after we came back to FIU, we processed the data, and you can see here our digital twin or elevation model. So we can have a very nice representation of the cells. With this data, we are using this data now for analysis, eventual underground erosion. You can see here on the image, you can even see the scar rains. And also we are using machine learning on this data to detect some potential potholes that might be underneath erosion. But now we're gonna even further. Now we did the aero mapping, so we have the idea of automate this process using a ground penetrating radar. So the cell is very large, so what we are doing, we are getting a off-the-shelf ground penetrating radar installed in a autonomous platform. So we're going to take this platform to the site. The platform is going to scan the underground. It's going to build the digital twin of the underground conditions. And now we can compare both surface and the underground surface and we can start predicting. And the idea is to automate this process. So the system is going to be completely autonomous. And then the user is just going to press a button. The scan is going to happen. And we're going to automate also the post-processing that usually require a specialist. We're going to try to provide 3D images for them. Another project that we are doing in terms of environmental mapping is automate inspections at WRPS. So WRPS is the only deep radiological depository in America. So it's a mine with long shafts and tunnels where the waste is stored. And continuous monitoring is crucial to improve safety and ensure compliance with environmental regulations at WRPS. WRPS has a problem, or the characteristics of WRPS that is a mine salt, and with time, this salt is going to start close due to the pressure of the earth. And then we have to have daily inspections, people walking around, looking this close rate. They also have sensors that monitor this close rate as well, using strain gauge. But when the salt moves, the cables snap, and then it's being some sort of burden to replace those cables. So our idea is to use a Lidar scanner in a mobile platform to be able to scan this. Of course, there's so many challenges of it. The mine is very long. They have shaft, access drift, waste disposal. But our idea is to complement existing geomechanical monitoring program at WRPS, developing technology for them. Also, other challenges, GPS denied, so localization is a challenge. We have monotonous structures. The tunnels are the same. There's no many features for us to do our localization in the long shaft. Another also challenge that we have is to make this tool meaningful to WRPS inspection, because you don't only need to capture the data, but you have to make sense this data to the inspection and provide them in a way they can inspect and try to perform their task. So we have several innovations. So we start with planning. We're using sensor fusion. There's so many sensors that we carry around in our module. And then we are creating diagnostic sensor data that has already his own computer acquisition. You can just mount to any kind of platform, aero or ground, and even wearables, and it can perform the work. Also, we are automating the process. It's a very cumbersome process when you get those point clouds and try to make the whole map mining. We're automating that. And then we're using machine learning and GPUs to analyze this data, creating alarms, and in a way that we can provide this input to the inspectors. Also, in terms of the data, we are creating time machines and automated storage to handle to automate the process and in this process. And for publishing share, we immersive reality and alarms that we are working on. So we're talking about the data operational challenges at WIP. So now we're talking about getting a LiDAR data to capture this data, but it's just the tip of the iceberg. So that is cheap, information is expensive, and that is raw and unorganized. Now you have to make this information, you have to give meaning and context to the information. So this is a big issue. So carrying a LiDAR is a straightforward task. However, automate the process and not creating a burden to the WIP inspection, dealing with this data is a considerable challenge that we are addressing in this project. So here also, we measure certainty of sensors. We are planning to use our sensors not only for visualization, but also for baseline measurements. So we need to make sure that the interactions of the sensor with the environment, we can understand these interactions and are able to compute and measure the displacement of the wall. So in terms of mapping as well, because the systems are very long shafts, so we have to create a very robust localization in a way that we can get our data that we collect and make sure that we are able to produce large, long maps, stitching them together and identify potential fails on this loop and go back and correct to provide large maps without GPS. So we've been testing these at FIU corridors. It's kind of similar to the same structure, very monotonous, no details, and long shafts. So here you can see, what important as well, that you have the LiDAR data that we collect. So those LiDAR data are structured, just point clouds, and now we need to make a challenge in making this data in information about surface and terrain for allowed us to have a safe traversability along the shaft, mine shaft. So on this process as well, we are working on onboard terrain risk awareness, because now if you're going to leave an autonomous, unsupervised platform doing the work, we need to make sure that the platform is not getting in trouble, because the platform getting in trouble there, we need to send a rescue crew to retrieve the platform, and then you become part of the problem or the solution. So what we are doing, we're using machine learning to identify traversability conditions and terrain conditions, and the platform not only get obstacle avoidance that was typical in most systems we use LiDAR, we have also terrain awareness, and then we look what type of terrain, and the platform tries to avoid mud or obstacles that can get stuck. You know, in the sense that as the platform will walk on the mine, the platform is going to get smarter and it's going to learn how to avoid potential pitfall in the mapping process. So, as I mentioned, capture the data is something very straightforward. However, make this data in actual digital twin. What we're talking about, that get a point cloud and make those point cloud in actually surfaces. This require a lot of pre-processing that we're trying to automate that as well. So you can see here to produce this data, we just have a LiDAR in a cart that we walk around. So that it cannot be more agnostic than that. That doesn't require any type of platform. You can see here the LiDAR and the computer, but in our process, our package integrate all of that in a 5-pound scenario. Not important also along the surveillance, especially if you want to do this over time, is to be able to create a semantic map of the environment. It's not only get a point cloud now, but identify corners, corridors, doors, and those along the map. And those can be used over time to recalibrate your map and make sure that you have a consistent analysis of the environment. Also, the LiDAR data usually produce 1.2 gigabyte per minute data. It's a lot of data. So also we try to alleviate the burden at managing this data. We use network storage in a way that the platform walks around, come back, this data automatically goes to the database that can be retrieved, and the operator doesn't have to deal with memory cards or copying the data. And sometimes the data takes like 15 minutes to copy itself, and then on this process is going to be automatic, and the user, the inspector, can go to his desktop and find all the histories of the scan data over time without having to actually deal with the data. Our network storage has multiple drives in RAID, in a way that if one fail, we have redundant data to make this data safe. Biggest problem then when you talk about automated inspection, collect the data, now we have this data over time. Every time you go back, you have this massive amount of data. So how can we provide tools using machine learning that is going to evaluate this data over time and give the inspector areas that changes has occurred to automate the process instead of them has to go point cloud by point cloud, analyze this data. And also we are using GPUs. The amount of data is so large that we have to use very powerful GPUs to process these in a fraction of time. In terms of deployment, we are in conversation with Sandia National Laboratory. They have a project to evaluate technologies at WIP, and then what we're going to provide our sensor to them, and they're going to perform the deployment for us. We're going to attach our sensor in their platforms, and then we're going to contribute to their task. Of course, capture the data is something. Now we have to analyze the data. So we talk about virtual reality, and when the inspector can go to his office and perform a virtual inspection of the facility, everything remotely, and compare changes over time. And also, we are considering augmented reality in a way that we not only are able to get the close measurements, but now when the inspector are walking the platform and he sees the walls, now we can project the data to the wall, and now we can have a assisted inspection that he walks around, and then he get the inputs from our time machine. You can see on the walls. We can even mark where dangerous parts, where the growth has increased. In a way, we can assist that. Also, we're using machine learning to recognize objects. That can help us, because every time we walk around the facility and we see the same object all the time, that help us to align our maps over time and get a better maps. In conclusion, digital twins technology are useful tools for decision making because it permits inspection to take many spatial data and trends into account. Consequently, managers can make more optimal, safer decisions based on up-to-date, abundant, and reliable data. And you can see here, the digital twins can automate this process, document the changes in a way, but there's a lot of challenge incorporating this to the inspector day life. Remember, people used to walk around and take pictures and look things. Now we have to make a robot doing that, collecting this data, but now we need to provide tools to automate this process, because also we don't want the burden of have to hire a robotics crew just to do the autonomous. The autonomous is supposed to be automated in a way that we collect the data, and then the data itself processes itself and shows to the inspector, and then we don't increase the burden in the operation. Yep.
Very good. So just to, we have about 10 minutes or so. So really quickly, a lot of the work is done by students. So, our DOE fellows, LM fellows, and our research assistants contribute to all the work that we do. So specifically to the fellows program, as I mentioned earlier, they're part of the technology development and deployment through their summer internships. They work on the problems during the summer. They bring the problem back to FIU, and then we contribute to optimizing or improving the technology so we can deploy it to the field, during the next summer. So as part of the program, as you all know, in some research at FIU, summer internship participation that our DOE fellows conduct every summer. We have a induction ceremony as well as some of the poster exhibitions. Just numbers, 183 inducted fellows, plus the ones that are going to be inducted later this next month. 144 summer internships, almost 300 papers throughout the years at different conferences, 17 students hired by DOE National Labs or contractors, others hired by other federal agencies, local government, and over 110 hired by the STEM industry as a whole. Just quick pictures of our latest addition to the DOE workforce. Jeff, which was great to run into him at Pensacola. We were there last couple of days. He was representing WRPS, and it was nice to see students being part of this industry and contributing toward the DOE EM mission. Juan Morales, Tristan at some of the River, Silvina, started with NNSA as an NNSA fellow, postdoctoral fellow, and now with Lawrence Livermore, and as well as Dr. Hansel Gonzalez Raymat, that is at some other River as well. So that's just the additions in the last 2 years, and we continue developing the pipeline to support the DOE EM mission into the future. So with that, I believe that's all we have from our end. We do have some time for questions, about 5 minutes. We'll be happy to answer any questions you may have. For those of you online or anybody here in the room, we'll be happy to answer any questions. All the hard questions, I'll give it to Anthony, and I'll answer the easy ones. So anyways, so Walter, I'll turn it over to you.
Well, thank you, Leo. Thank you, Anthony, for the excellent presentation. Thank you for sharing all the information on all the videos. And I want to open up to the participants who are joining us today. If you have any questions, I know we have JP joining us from DOE. I think if you're still on the line, JP, I want to say hi. I don't know if you're dropped now. But yeah, thank you so much. Anybody has any questions for Dr. Lagos or Anthony?
All right, no problem, Walter. If there are no questions, that's it. We finished a little early, but we want to thank you for participating.
All right, before we end, I want to just remind you guys that in the chat that I put a couple of links to our feedback form. If you can please take about less than a minute to fill that out, it will help us select future topics for Tech Talks. So that's one thing. Also, in the same chat, there's a link for the Tech Talk event website where you can sign up for our newsletters, and we send you newsletters to inform you about future Tech Talks and the dates. Our tentative Tech Talk date for the next one is January 17th. We'll be sending information about the topic as soon as we have secured our speaker. But I also just want to thank you all for being here this morning, participating on our Tech Talk. I appreciate all the students that showed up at the conference room there. Thank you for being there, guys. Appreciate your support. And I'll leave the last word to you, Leo. I want to say goodbye.
No, thank you. Thank you, everyone, for participating. Thank you, Anthony, for being the co-presenter. And again, if you have any questions, you can always email us or send it through KMIT. I think you have a portal there as well, Walter, so we can use that platform as well.
Let's do that. Well, with that, this concludes our Tech Talk today. Thank you again for participating. Again, thank you to our speakers, Dr. Leo Lagos and Anthony, and all the students that make this research possible. Thank you so much, guys. And we are dismissed. Thank you very much.
Thank you, Walter.
Thank you.